Welcome to an Introduction to Science, brought to you by Parkbench Tutors and narrated by David Hopcroft. For more information about Parkbench Tutors, please visit parkbenchtutors.com. In this short podcast, we shall pursue ideas relating to relativity. Here we look at a new dimension which is referred to as spacetime. We are assuming that you have already watched the first podcast. We start by introducing the idea that there are three important concepts in science. They are referred to as invariance, causality, and distance. What do these mean? Invariance can be understood by stating that the laws of nature will not be changed if they are viewed from different directions, nor will they change from place to place. Gravity is the same force acting upon you whichever way you turn and face. This is known as rotational invariance. I can take my computer to any city and it will still work in the same way. This is what we call translational invariance. A mathematician, Noether, determined that if the laws of nature remain unchanged, then there must be some quantity that is conserved. For rotational invariance, we call this quantity angular momentum. And for translational invariance, the quantity is simply called momentum. There is a neat little example of angular momentum that may help here. As the Earth spins on its axis, it is slowing down as a result of friction with water and tides caused by the Moon. This slowing down effect amounts to slowing the spin by around 2/1000ths of a second each century. So if angular momentum is to be conserved, something else must happen. In fact, the Moon is moving away from the Earth at a rate of 4 centimeters every year, because the spin lost by the Earth is being transferred to the Moon, which then speeds up in its orbit around the Earth. This causes it to drift slowly away from Earth, so total angular momentum is conserved. Causality simply states that for two events to occur, where there is a cause and effect, then their order cannot be reversed. This will be important in our treatment of spacetime. If I use my bicycle to go to work, then I cannot arrive at work before I set off on my bicycle. At the moment, that might sound pretty obvious, but we shall see it is not always that clear. In the first podcast, we determined that time may vary according to how fast different clocks are ticking, and that distance is no longer an invariant quantity. We are looking for an invariant quantity to meet the requirements of the laws of nature. The suggestion was first made by Minkowski that we needed to merge space and time into a single entity. It is this entity which we are calling spacetime, and we are guessing that distances in spacetime will be invariant. That means that the spacetime distance must not change when we move around relative to each other. We need to try and put this idea into a framework. Let us suppose that I cycle to work, leaving my garage at 7 a.m. and cycling 10,000 meters to work to arrive at 8 a.m. By my clock, say my wristwatch, I take an hour to get to work. An observer travelling by at high speed will record a different time. We need spacetime to record the event, so the answer in spacetime is the same for both. What do we know about representing distance? The shortest distance is a straight line between 2 points, we have been told. If I am on a plane from Manchester to Jacksonville and watch the flight path on a screen, it will appear as a curve. The curved path is because the Earth is not flat, but the map projection is flat. The geometry of flat surfaces is Euclidean, the geometry we met at high school. It will not describe our curved Earth. The line representing the shortest distance between any 2 points is a geodesic, and we are looking to measure space-time. I might say it took me an hour to cycle to work, or that I cycled 10,000 meters to work. What I want to do is to merge these ideas, and so I need another dimension. Our everyday world is usually perceived as three-dimensional, but if we pause and think, we realise that any point would actually need four numbers to fix a position. We need latitude, longitude, altitude and time. The target we are setting ourselves is to have both the 1 hour and the 10,000 metres expressed as an invariant distance in space-time. What we are doing is not that hard. We already know that speed is distance divided by time, time is distance divided by speed, and distance is equal to speed multiplied by time. So distance and time are connected by speed. This means that all we really need is to have a calibrating speed. Astronomers already make use of a unit that expresses distance in terms of time, and so we are not doing anything really unusual. To astronomers, distance can be expressed in terms of light years, defined as the distance light would travel in a year. It is easier to try and visualize these things. We have time and space. We mark in 2 points as crosses. How far are these crosses apart if we use space-time as the measurement? We are looking for a distance which is measured in space-time. Here you can recognize a familiar triangle. It has a right angle, and the 3 sides are represented by S, CT, and X, where C is the calibrating speed that we are trying to determine. At this moment it is undefined. We are trying to determine S, and we need to know whether we can apply Pythagoras' theorem here. We will use the idea of Occam's Razor. William Occam was an English thinker from the 14th century. Essentially, he states we should not overcomplicate things. Just try the simplest idea first. In a minute you will see there are 2 possibilities. But first let us make 2 assumptions. Firstly, we will assume space-time is flat, and second, that it is the same everywhere. The 2 possibilities are s squared equals ct squared plus x squared, and s squared equals ct squared minus x squared. There are 2 possibilities here because we could use the plus or minus sign. There is no reason why it has to be plus. To see which it is, we must see if either of these will agree with causality. If I start off at O on my bicycle and arrive at B, my work, an hour later, then the event O must precede event A. We remind ourselves that on my bicycle, x is 10,000 metres and the time taken is 1 hour. But to the observer it can be different. However, s has to be the same even if x and t vary. Now we need event O to occur before event A. Using Pythagoras, every point on the circle is the same distance s from O. We have just selected 3 of these points. We should note where these are in terms of the axis for time. A and A' seem possible. The event occurs after O. This agrees with causality. A double dash, however, presents a problem. A double dash would be an event that occurred before O. By causality, this cannot be so. So we must now reject Pythagoras with a plus sign. This leaves us with the minus sign in the equation instead. This time we get a curve that represents Minkowski space. Does this now meet the requirements for causality? All the points for A lie on a curve called the hyperbola, and all points for A are in the future compared to O. This satisfies causality. So we now need to find the calibrating speed. Before we do, we have to deal with what seems to be a potential conflict. There will be 4 curves that can be drawn. They're shown here. 2 of these curves cross the spaceline and suggest B might be occurring before O. Here is the way out of this. The dotted lines represent events that are a distance ct from O. For B to influence A, it has to travel faster than C. Assume that C is the cosmic space limit. Now an event would have to break the speed limit to violate the cause and effect principle. We are now attracted to the idea that c might be the speed of light, but we are not quite there. We return to the train analogy. On the train, space-time is c small t for the person on the train. For the observer, space-time is s squared equals c large T squared minus v large T squared. Now we are using our equation with minus sign. S should be the same for both journeys. So we can say that c small t squared is equal to c large T squared minus v large T squared. The enhancement formula will become 1 over the root of 1 minus v squared divided by c squared. This we have met before, and it only works if c is equal to the speed of light. At this point we can look again at the aging problem and travel through space. A person on Earth moves along the line following the time axis. A person travelling in space moves along the curved line, the green line here. The space-time for both is determined by s squared equals ct squared minus x squared. Now for the Earth traveller, x is equal to 0, so this must be the longest path. For any other space path, the space-time is shorter, since we have to subtract the x contribution. This ends our podcast on space-time, brought to you by Parkbench Tutors and narrated by David Hopcroft. Thank you for watching and for listening. We wish you success in your studies. For more information about Parkbench Tutors, please visit parkbenchtutors.com.